Hello everybody, my name is Juan Martinez from Odin Solutions, and in this video I'm going to introduce security, privacy and trust pillar IoTCrawler architecture. This project was conceived with the objective of providing the next generation of internet search engines focused on IoT information. This way, IoT devices or their information can be crawled, discovered and searched with the added value of doing this in a secured and controlled manner. Let's dive into the design and implemented architecture of IoTCrawler. Following a bottom-up approach, we can count with the following layers: micro layer, domain layer, interdomain layer, internal processing layer, and exposure layer. Finally, since IoTCrawler has covered the topic of security and privacy from a traversal point of view, we have in this architecture the security, privacy, and trust pillar. This is a traversal layer which provides IoTCrawler architecture with mechanisms for authentication, authorization, and privacy for the access to the data. Security and privacy governs the interactions of the components of all the layers defined in the architecture. For the micro layer, IoTCrawler defines a secure bootstrapping enabler for integrating IoT devices into a security domain. To do so, they must employ low-level authentication protocols such as PANA or CoAP, transporting EAP, Extensible Authentication Protocol. In the domain layer, we find an authorization mechanism which is based over capabilities and called Distributed Capability-Based Access Control, DCAP-BAC. It decouples the well-known SACML framework into two different phases: the decision and enforcement. Once an authorization decision is positively made, an authorization token is issued. It is called capability token. This token is a signed JSON document with the advantage that it can be easily validated without querying any other third party. This token has a validity time, and it must be presented every time a request is made for the MDR. The PAP proxy is responsible for capturing this request and perform the corresponding validation over the capability token. If the authorization is granted, then it forwards the request to the MDR and the response coming from this later to the one that requested this information. Finally, at the interdomain layer, we have proposed a mechanism based on blockchain networks and more specifically on a smart contract. This is integrated with the interdomain authorization proposal and assures that the authorization policies are consensual, tracking also the performed authorization operations. This pillar also contains an identity manager responsible for handling the different entities, users, devices, or services, along with their attributes, as well as the authentication operation, and CPABE, which stands for Ciphertext Policy Attribute-Based Encryption, an encryption technology for broadcasting information in the shared media in a secure and privacy manner. Let us illustrate the usage of these security components through a diagram. In this example, a component, user, or service intended to access the MDR information must first accomplish an authentication and authorization process before querying the MDR. The authentication phase is made through the identity manager, which basically consists in checking the credentials received and matching them with the existing information in their corresponding database. If a positive answer is issued, an authentication token is also transmitted inside it. On the other hand, the authorization is a more complex process, which requires the interconnection of the capability manager and the XML framework. The capability manager is a component which receives authorization requests. It transforms these into XML format, which is forwarded to the policy decision point of the XML framework. This latter validates these requests against the XML policy file, and it issues a verdict. If the capability manager receives a positive answer, it generates a capability token, a signed JSON document which also contains a valid period of time to be used. A user or service which receives this token proceeds to make the corresponding request to the MDR, including also this token. The PEP proxy captures this packet and validates the token. If the answer is positive, it forwards forward and back the corresponding messages between this user or service and the MDR. It is also possible to use the PEP proxy to encrypt the information to be stored in the MDR. To do so, the data provider must specify an encryption policy inside the NGSILD representation. This way, the PEP proxy encrypts the information according to the policy, preventing non-legitimate consumers to extract this information. CPABE presents a very flexible way at representing encryption policies. It is based on attributes, so we can express any combination of them. An example of a CPABE policy is presented in this slide. The encryption policy is a combination of two attributes, role equals admin and floor equals first. This means that when a consumer uses his CPABE key to decrypt the information, he will be only able to decrypt it if his identity and the corresponding attributes matches this specific policy. In this example, only the first and the third consumers are able to do it, but not the second one. This example can give us an idea of the flexibility and granularity this encryption technology provides. The last slide of the security section deals with the integration of both the authorization enabler and redefined and the blockchain technology. So far, we have integrated both of them so that we are able to check if the policy file has been tampered. Additionally, we take advantage of the blockchain technology not only to check if the use capability token is valid or revoked, but also to track every use of it. With this slide, we finish this tutorial onto the security and privacy pillar. I hope you have enjoyed this tutorial, and thank you very much for your attention.